Hello, hello. Hello, I'll be right there if you, I don't know if you can hear me. Hang on. Good to see everybody. Can you hear? Can I get it? Oh, good morning. Thank you, Benitez. Hi, Amari. I'm great. Thank you. And I take it that means you can hear me. Hold on. So, yes, good morning. Um, And good morning, Jean. Awesome. Thank you. Good morning, Vanita. Good. Hi, Matt. Oh, sorry. Hi, everybody. Good morning, Jean. Good morning, Amelia. And if one of you could let me know, does this mean that you can hear me? Good morning, Gabriel. Good morning, Melanie. And we can hear you. Great, great, great. Thank you, Simon. Okay, wait, sorry. Now you're all here. Great, great, great. What, Vanita, Amelia, we can hear you. Great. Oh, sorry. Hold on. I'm responding to a direct chat. Okay, we're gonna start in a second. Just give me, I mean, we are starting, but hold on. And um, okay. Um, okay, more people coming. We will start in I mean, we are starting. Blah, blah, blah. Um, main agenda item today is average acceleration, the concept, and the homework sheet. Bear with me. Okay. And remind me, we may have time in the middle of today. I owe you a bunch of points. Like I think I've now fallen one full class day behind on getting you back. So good morning, Vicky. Thank you. If you just turned in something recently, like since last class, you have not gotten it back yet. That is true, and that is not personal. That's me. There may be time in the middle of today for me to get it back, but I am a little bit behind right now, so please bear with me. Um, okay. What we're gonna do today, what we're gonna do today is start walking through the concepts of average acceleration and instantaneous velocity as they arise in homework 4. Bear with me while I switch the screen and pull up homework 4. But while I'm doing that, I will say, just a quick recap, last time we did homework 3, which was the train of thought, Gedanken experiment, thought experiment. And that was conceptual. And today we're back to math, thematical looking things. And last week was about the nature that, well, was about Galileo's principle of relativity. And we introduced the first 3 forms, as I see them, the first 3 forms of Galileo's principle of relativity. Each next form is like a logical restatement or almost inference from the last form. In other words, they're all ultimately the same logical content, but each next form is a different way, a deeper way of seeing the implications of the principle. And the ultimate principle, just to review, the ultimate principle that we established last time is that velocity is a relation between 2 objects. It is never a property of a single object. That is what we mean when we say that velocity is relative, that you can only meaningfully discuss the velocity of one object relative to another. You can never just talk about the velocity of an object, like in space or in the universe or something like that. And therefore, whenever you talk about, sorry, I'm just trying to pull up therefore, whenever you wish to measure or uh, um, assert or compute with the velocity of an object, you must first specify the other object to which you're comparing the first object's velocity. When you always need a standard of comparison. And in physics, that standard of comparison, and you may want to write this down. I know I'm just talking right now, but as part of the recap from last week, the key thing I'm saying right now is that like the standard of comparison to which you use when measuring the velocity of an object, the second object to which you compare the first velocity, that second object in physics is called a reference frame, or truly the coordinate system that emanates from or originates at that second object is called a reference frame or a frame of reference. In order to do a physics problem, you must specify first a frame of reference. Okay, I'm going to say that this is for notes. I'm not writing it down because I don't want to confuse the things we're about to get to. But define a frame of reference. I know two people in the waiting room. Oh, and I love Gabriel's thing. A frame of reference is a coordinate system and perspective maintained by an observer regarded to be at rest, or regarded to be, or hypothesized to be, declared to be stationary. I'm going to say this again. A reference frame is a coordinate system or a perspective, and a perspective maintained by an observer declared to be at rest. And you can put in the direct chat if you need me to say that one more time. Or, and of course, you can replay the video, and of course, it won't be in the PDF, but it'll be in the video. But the importance of that, and then we're going to move on to average acceleration. What I mean is, awesome. Hello, Annie, and hello, Gabriel. Oh, yeah. Hold on a second. Sorry.
Hi.
Oh, hi. Okay. I didn't say oh yeah to you. I said oh yeah because my phone just went off. Let me put my phone on focus. Sorry. It really should be like put my phone on unfocus. Oh, I guess it means that I'm focusing, not the phone is not focusing. Okay. A frame of reference is like a crucial idea to physics. It is the perspective to which all other velocities are compared. So it is the zero velocity perspective. If you really think through what we were saying last week about Galileo's principle of relativity, and it's going to come up again and again and again, it's going to come up in more forms, like we did 3 forms last week. There's more forms to come. I've mentioned every chapter or topic we do in physics, like for the rest of our life, is yet another form of Galileo's principle. So it's not going away. It underlies everything we do. And so it's okay if, or in fact, it's necessary that you sort of like catch on to it in layers. It's not expected that we catch on to the whole thing at once. But one thing I want you to start catching on to with Galileo's principle of relativity from last week is that all velocities are in the eye of the beholder, right? There are no objective velocities anymore. The sun is not objectively going 0 miles per hour, nor is it objectively going 65,000 miles an hour as it is past the Earth, nor is it going objectively 650,000 miles per hour as it is past the center of the galaxy. Like what the sun is doing, or what the Earth is doing, or what I'm doing is relative to whatever I choose to compare myself to. And whatever I choose to compare myself to, tacitly, we say is stationary, right? So if we say that the Earth is going 65,000 miles an hour past the sun, right, then we're using the sun as a frame of reference. And if you think it through, you realize by using the sun as a frame of reference, we're tacitly, or we're declaring the sun as the zero velocity. What I want you to see now, though, is we're just declaring that. We are not saying that the sun objectively in the universe is like a special actual zero. We're saying when we compare the Earth to the sun, we call the sun zero, we call the Earth 65,000 miles an hour, or other way around. If I'm doing an experiment in a lab on Earth, then I say that the lab attached to Earth is going at 0 miles an hour, and the ballistic that flies through the lab is going 300 miles per hour, or whatever, right? So you always need to, we're really saying you have the right in physics and the responsibility before you start solving a problem to specify what is my frame of reference. And that means 2 things. What object am I saying is still, and thereby comparing all other speeds to it? And then then if I'm choosing the lab as the still frame and I'm comparing my ballistics or whatever to the lab, then I imagine a coordinate system like, X, Y, Z axes, whatever, how right now we're still in one axis, but I imagine an axis whose origin is like the center of the lab. And whose arrow goes positive in one direction and negative in the other. So from now on, like to do physics, you are allowed to choose your coordinate system, but in fact, we're saying you have to. If you are not conscious of what your coordinate system is in any given problem, or if you are like start switching around without realizing what coordinate system you're in, that's when physics goes bananas. So it's sort of a recap. So train of thought is meant to get you into the mindset of that. The conclusion is this Galileo's principle of relativity. From now on, all velocities are relations, not properties. They are relations between pairs of objects. They are not properties of one object. Therefore, anytime we talk about velocity from now on, we have to start by establishing a frame of reference, even if it's so redundant after a while that we all kind of know which one it is. We still have to have it consciously in our mind. And then what does this all have to do with math and the problem solving that we're now going to get into in sheet 4? Because I know we started math and then we did this left turn to like concepts, and now we're going back to math, and the math is going to involve calculus. And it will be a possibility that for many of you at many times, you'll sort of be doing the math thinking, what does this have to do with that side road? Like, why did he waste our time with this Galileo stuff? Like, this just looked like math computations to me. And what I'm here to tell you is sometimes you won't see at first, you won't see where the relativity implications are at first, maybe, especially when you're deep into a calculation. Sometimes you won't see explicitly how it connects. But a lot of times what I'm here to say is, especially if you're having difficulty starting a problem, it's this concept of relativity and choosing your frame of reference that ends up being the key to starting a problem and understanding a problem and seeing how, and doing the physics thinking to set up the math before you get into the math. So bear in mind, it will get bigger and bigger, but in the back of your mind, just bear this idea that velocities are relative. That's how we understand them. And when in doubt, that's a thing to think about when you're trying to navigate the subtleties of a physics problem. If nothing else, and then I'm done with this rant, if nothing else, from here on in, when you are on step 1 of solving a physics problem, step 1, diagram and fact pattern, from here on in, I've mentioned that the diagram, a big part of it is labels, right? From here on in, one of the key labels you will put in many, many diagrams before you do anything is you're going to make clear what the coordinate system, the frame of reference is that you're operating in. Like, we already have to do that, make clear what direction is positive, what direction is negative, but it's going to be more and more necessary and apparent that you specify, like, okay, I'm in the lab frame of reference. The lab I'm designating as moving not at all, and the lab is attached to Earth. I'm designating that as my perspective. All my velocities are going to be compared to that. Like, that's okay. So we're going to move to math, back to computations now. And everything I've just said in a way is like in the back of your mind churning, and it'll keep coming up again, but I don't want to jostle you. We're going to go back to math now, and explicitly my focus will be solving the math looking problems of sheet 4, homework 4, average acceleration. That's what we're turning to. And again, for anybody who just joined or whatever, if you turned in something in the last 5 days and you haven't gotten it back, that's correct. And I apologize. It's not personal. I owe you stuff. Okay, let me just pull up. So we're going to go to, yeah. Okay. So I'm going to switch the screen for a second. Well, so we're talking about this sheet. I'm going to switch the screen for a second so you can see what sheet we're talking about. Oh, wait, something in the chat. Oh, yeah. Oh, wait, okay, something in the direct chat. Everybody can still turn in homeworks. We're getting to the point soon where if a homework comes in late after, if a first draft comes in late after the original deadline, we're getting to the point now where I might not give you all the points, or I might not give you an opportunity, like even if you do full revisions, if a homework is coming in late now, if a first draft is coming in
after the original deadline. We're soon getting to the point where that might mean you can't get all the points, but you will still, everybody, you'll still get the majority of points. It's still absolutely worth your while to turn in any homeworks that you have not. Absolutely. And again, I still owe you some stuff, some of you second drafts and whatnot. Absolutely worth it. Okay, good. Okay. And thank you for the thank you. Okay. So I'm going to switch the screen for a second just so you can see what sheet I'm about to do. So it's this sheet. Yeah, in fact, I'm going to sort of fly through. Oh, I don't know what, I couldn't preview the file. Well, I'm going to quickly go through like the exercises and not do the 5-step method. I'll save the 5-step method for when it gets more intense. Hold on. All right. So you can look at that so that's what we're talking about. I'm going to start, but I did have an announcement, one more announcement before we. Um, Another bad style. I just ordered new styluses. I prefer those of you keeping score at home. Um, all right. And I'm writing, I know you can't see the tablet right now. I'm about to switch again so you can see the tablet. The main thing I want to get to here today is number 3, even if I don't get much farther than that. Okay. So we're about to do this. First of all, raise your hand, electronic hand, if you're like still with me, if you understand what's about to happen or what's happening so far in the class today. Like if you're with me. Great. Thank you, Gabriel. Thank you, Vicky. Thank you, Mariam. Thank you, Vanita. Thank you. Awesome. Thank you. Thank you. What was that? Oh, wait, who else? Thank you, Jocelyn. All right, that's good. Thank you. Okay. Awesome. That's good enough for me, I guess. And if there's somebody, if those of you who are not raising your hand, if you have an issue, please let me know in direct chat. But okay, because we're about to go, I'm going to switch the screens around. I'm going to go to, I'm going to, look at the questions while I write down the answers for you. I'm just going to bang through answers and you're going to stop me for the first couple because I think they are sort of reviewish. I'm just going to bang through answers so that you have them and you're clear and you stop me if you don't understand or don't agree with something. Okay. But before I do that, okay, I have this here. I am going to pause the recording for a second. Well, yeah, I'm going to pause the recording for a second and tell you something off topic. Yes. Okay. The recording is back on. So now we are going to homework 4. Switching the screen again. Okay. So very quick review. And I'm not going to do the 5-step method. I'm just going to bang out answers here, like I said. But right. But I will say this is a little minor example where this whole problem only makes sense if you first specify a coordinate system, a frame of reference, right? So I'm just gonna draw a little quick diagram here.
So this is like a simple problem, right? But just to be clear, like I'm establishing, all right, I'm looking, oh, and I totally wrote it backwards. I'm sorry. God, I am sorry. You get the point, but right, I totally did it backwards. It's Berlin is north of Rome. So this is the, now strictly speaking, all right, so this is an example, like this is the reference frame of the problem of Rome. Like I'm looking at the problem from the perspective of Rome. Rome is the center of my, or is the origin of my coordinate system. Berlin is to the north and everything that, so well, I'm calling north positive, I'm calling south negative. So I'm trying to specify a couple of things like where zero is, where positive is, where negatives, but also now to be super clear, and this is a subtlety, it's not going to affect my answers in this problem, but when I say this is the reference frame of Rome, in fact, I'll write it here. Okay, very important point. It won't affect this problem, but just so you can see how this is going, is that we're in Rome's reference frame now, okay? But here's the thing, a reference frame or a frame of reference in physics is not a place. It's not a place. It's a perspective, which means that, yes, the reference frame is like the origin of it is Rome. It's like the Rome reference frame. It's based on Rome. But what it's based on about Rome is not where Rome is. It's based on how fast Rome is moving. This reference frame is defined and attached to the velocity of Rome. And you might say, what do you mean the velocity of Rome? I thought Rome was a freaking city. It's just sitting there. Well, it's on the earth, right? And the earth is in the universe, right? What we're saying is, yeah, we're going to say that Rome is just sitting there. We're going to say it. We're going to look at the world as though Rome is just sitting there, even though remember, half of our brain totally knows that that's not the case, right? If we were comparing to the sun, Rome would not be sitting there. It'd be moving at 65,000 miles an hour, yada, yada, yada. So what we're saying is, okay, we're getting into a perspective where we look at Rome as fixed and stationary. Therefore, anything that has the same velocity as Rome. What velocity? I thought it was zero. Right. Anything that has that same zero velocity as Rome, anything, whether it's attached physically to Rome or not, whether it's close to Rome or not, anything that has the same velocity as Rome is in the same frame of reference as Rome. So at the risk of possibly confusing you, but trying to get all these ideas out as early as I can, Berlin is a different location. Berlin is a different position in this coordinate system. Like it's, it's to the south, and we're going to do a calculation in a second. But Berlin is in the same frame of reference as Rome because Berlin is not moving past Rome, right? If you were to stand in Rome and look at Berlin, like through a telescope or whatever, or on a computer monitor, you don't see Berlin moving. It's still compared to you. And right, and even if you were standing on the sun, watching Berlin and like, wait, Berlin is moving through the space, like past the stars and everything at 65,000 miles an hour, you would see Rome tracking along the same way. So whether the real point I'm trying to make now, even again, is a reference frame is a perspective defined by, and you might want to write this in notes or something. A reference frame is a perspective defined by velocity, not defined by position. So it's not a perspective like art. I mean, it's very related in that, like, it's related, but it's not the same thing. In art, if you stand farther away from a painting, I mean, in visual arts, right? Like you stand away farther and farther from a painting, the painting looks smaller and smaller, and maybe even like the colors blended. So like in art, in visual scenarios, perspective is defined by where you are. That is not what we're saying here. We're not talking about optical sight lines or anything like that. We're talking about motion. always in physics. So from here on in, when I say the frame of reference of da 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 da, I mean anything in the universe that's going the same speed and direction as da 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 da, whether they're attached to each other or close to each other or not. All right, enough about, but just to note. So we've got, so the first thing you always do in all these kind of problems for now is like, what is my frame of reference? What is still in this problem? And what's still in this problem is Rome and Berlin. Okay, now, is that going to wildly change the calculations I'm about to do for this problem? No, because it's a very quick review. It's simple. So I'll just do them now. Okay, so I'm not trying to, but like, so I'm just going to bang out the answers. You'll stop me if you don't like them. Oh, I think I just saw a hand. Wait, sorry, I'm back and forth between screens. I think I heard a hand. Was that a hand? Is that a, if that's a hand?
Yeah.
Oh, Annie, yeah, sorry, go for it. Sorry. Yeah.
I just want to clarify something. So basically, if there are two things that have the same velocity, even though they can, like, even though they're like not attached to each other, they are in the same reference frame. Is that what you're saying?
That is exactly what I'm saying. I'm not being sarcastic. That is exactly what I'm saying. But I'm glad you just said it in your words because, yes. And I'm glad you just clarified because I'm saying it loudly because I think it is surprising. Like it is a new, and it's super important. And I'm glad you just put it in your words. You nailed it. I hope that helped other people, what Annie just said. It is a big deal and it's not obvious. It is true what Annie said. And it's simple, but it's not easy. So exactly what I mean, and we're going to get into that. But yeah, things don't have to be attached to each other or even close. Like right now, I'm in the same reference frame as China. Like I am in the like America and China. They're not the same place, but they're the same frame of reference because they're both going the same velocity, i.e., same speed and same direction. 100% right. Thank you. By the way, I need to open up a portal for that too. Just when people like echo or mirror what I'm saying and show that they, like that, I think that's great for everybody. Okay, I won't overdo it, but yes, well done. Okay, and again, and all, okay, I'm so please understand that this conceptual, so basically all of you, if it makes it less confusing to deal with me in this class, there's two threads that always go through physics. There's the conceptual thread and the computational thread. The hard part is keeping them, seeing how they harmonize with each other. Like that's our job as physicists. Sometimes it seems like one is over here and one is over there. And so that can be confusing. Like what is the algorithm even talking about? Right? Like, because I'm about to go back to the problem and you're going to see guys like that what I'm about to do, it doesn't even directly seem to apply what Annie just said. But they're parallel threads. They're threads. They keep weaving in and out of each other. And I promise you this, when in doubt on the math, go back to the concepts. It's the concepts that make physics, not the math. Okay, sorry. So I'm babbling too much. But yes, Annie, again, I'm sorry.
Um, yeah, I'm sorry. I don't mean to like distract you from doing the
No,
problem,
you're
but
good.
okay. I was just wondering, like, so if there are like, if we're looking at two stars within the same galaxy, but the galaxy is like shooting outward like through space because space is expanding, but also within the galaxy, like they're moving together, like the stars, the planets are moving like as a galaxy, like together through space, but also like within the galaxy, they're like spinning and like getting further apart. So would the two stars from the same galaxy be on the same reference plane if we're talking about like the universe, like the expanding universe as a whole?
Again, a really good question. Yeah, now this gets into subtleties. Here's the quick reality of that is that, of course, you're absolutely right that in reality, whatever that is, stars are in motion all the time, just like our sun. And every single star is actually moving relative to every other. Like, yes, the universe is expanding and galaxies are spinning. And it's a huge coincidence if two stars happen to be tracking along together in the same speed in the same direction. And if they are, it's not going to be continuing for very long. Because really stars, the paths that they tend to be on are curved paths almost by necessity. So you are right that stars tend to, any given two random stars tend not actually to be in the same reference frame as each other. That is correct. And if we're really doing astronomy and we're looking at them and we're sort of close to them or literally studying them, we have to really take that into account. Now, the subtlety that may confuse people, but just as long as you're asking, which I'm glad you are, the subtlety is that because we're so far away from stars, the weirdness is that from Earth's optical perspective, like from that perspective, like from the rough, informal visual perspective of us taking data on Earth, when we look at all the stars in the sky, the constellations, they're all so far away from us that their movement relative to one another looks barely detectable to us unless we're like tracking really carefully and really telescopically over time. Like this is where visual perspective and physics perspective get a little bit like jumbled, because like what it looks like to, because just like airplanes, like they look like they're moving really slowly across the sky because they're so far away that every set of miles that they traverse only takes up a tiny percentage of our visual field. So it's harder to detect motion farther away. So when we're looking at stars from here, like with our naked eye, they look like they're all moving together. So depending on the context, depending on what zoom, focus we're making, when we can talk about stars, we talk about all the constellations as though they are one frame of reference, the reference frame of the zodiac, like because they do seem to us like they're. And for a lot of contexts and a lot of on the ground, like if you're just trying to predict eclipses of the moon or things like this, phases of the moon and eclipses of the moons of Jupiter, whatever, we can treat Scorpio and Sagittarius and Orion's belt and all that as all fixed to each other as one frame of reference. And we do. Informally or at this level, we treat them as one frame of reference because we can get away with that at this context. But once you're getting into the details and getting closer, then Annie is absolutely right. Then no, every one of those stars is its own frame of reference. Absolutely. So maybe I'm saying too much for many people right now, but I appreciate the questions. And sorry, I'm seeing in the direct chat. So apparently this is lighting up something in somebody. Oh, okay. Wait. Oh, yeah. Okay. So I'm gonna go backwards in the chat and I'll go back. And this is the class, by the way. Again, like this is not off. Nobody should be apologizing. If any of the rest of you, if this is triggering, I hate that word. If it's doing anything in your mind at all, making you even care about physics at all, great, and put something in the chat. This is not off the topic. It is the topic. It's I'll get back to the sheet in a second. But so for example, there's two things in the chat. One is Annie's public thing. So yes, what you do, the physics is super dependent on perspective and I'll say context. She says objective, sure, objective context. But the big lesson in Galileo's principle of relativity is that at least velocity is definitively, explicitly dependent on your perspective. This is what's so powerful about physics. You've all always known this, and you know this from other social sciences and things in life. Like you've heard a million times, oh, perspective matters. What we're here to tell you is it doesn't just matter in a soft way. It's not just kind of like an excuse to say, well, I have my opinion and you have your opinion. No, in a very strict way, in the specific way of velocity, velocity is meaningless without perspective. It's not just taking into account perspective. You literally cannot talk about velocity until you specify your perspective. So it's explicitly scientifically dependent on perspective. And I'm going to get to the direct chat thing in a second. And this is the art of physics. It's really, and I'm telling you, you can see I'm getting excited, right? It's layers and layers and layers of an onion, seeing how powerful this perspective thing is, and seeing that it's a scientific idea. It doesn't mean, well, I have my science and you have your science. We're saying within science, certain ideas are I have mine and you have yours. And even there, it's not just me and you. It's like, as long as something is moving at a constant velocity, as long as something is not accelerating, which is why we have to get into acceleration now, as long as something's not accelerating, then it is legitimately, it can be treated as stationary as legitimately as anything else that's moving at a constant velocity. Now, and there's still something in the direct chat, but no, so we have to choose our perspective, and no one constant velocity perspective is better or more correct than another. We're not just choosing like for convenience. I mean, we're saying it is a choice among
the constant velocity objects. Remember, this all comes back to the first form of the principle, which says the laws of physics are the same at all constant velocities. It doesn't say they're the same in all situations. It says at all constant velocities. So please note too, and this is really what I love about physics, perspective is huge. Perspective plays an enormous role in physics, but it's not the whole game. We're not saying there's nothing objective. We're not saying nothing transcends perspective. If we were saying that, it wouldn't be science. There are things that transcend perspective that we all have to agree on. That's what makes it science. The interesting question is, what are those things? Turns out velocity is not one of them. Velocity is on the path to one of them. So science is about recognizing that just because something says, just because you make a measurement, that doesn't make it objectively true. But similarly, that doesn't mean there aren't objective truths. Now, last, because there's something in the direct, so for example, in the direct chat, so I won't mention names, but it says a wonderful question in the direct chat, is there anything in the universe that does not move at all? I'm here to say, if by that you mean objectively, is there anything in the universe that I would say it does not move in like a special way that I wouldn't say it about other things? No. There's nothing in the universe that has, that's the point. I mean, that is a great question. The huge revelation of Galileo, and we did not know this before Galileo, or we didn't think this way before Galileo. But right, there's nothing, there's no center to the universe. There is no center to the universe. That is what we were saying. That you can, or everything is a center. You can declare anything you want as long as it's cruising, as long as it's constant velocity. You can declare the sun to be the center of a universe that we call the solar system. Like, what is a solar system? It's the system of things going around the sun. But that just means that the sun is the center of that. The sun is still, if we want to say, in that system. But meanwhile, that whole thing is revolving around the galactic center at 650,000 miles an hour. And then, as Annie pointed out, our galaxy is one of many that's revolving around, the center of the supercluster, or the Virgo supercluster that we live in, and on and on and on. We are definitively saying two things. And the reason I love these questions, even if I never get back to the sheet, I will get back to the sheet. But this is physics. This is what's exciting and cool about physics. And I'm not just a madman. I am a madman. But it's not just like rant. Oh, everything is chaos. Oh, there's no truth. No, there is truth. Everything is not chaos. But if you thought absolute velocity or absolute stillness was one of the centerpieces of truth, that's wrong, we're saying. And it's important to realize, yes, there's no center to the universe. There's any object you can say is sitting still, but there's no one object that we should say it any more than any other object. I hope the direct chat person is hearing me say that. And why it's a good question. If there's any of you in the room who's daring to think, I mean, look, you might think, Gaverbaum, go on. But if you're thinking, how could someone ask that at this point? Like, don't they get that? No. To ask if there's anything in the universe that does not move at all, please understand that for 2,000 years of super progressive advancements in astronomy, mathematics, and natural philosophy, for 2,000 years, civilization progressed beautifully and precisely and predicted all the like the phases of our moon and eclipses and all that stuff and the rising of Sirius and the flooding of the Nile. Like, we knew what we were doing with the relationship between heaven and earth for 2,000 years, and for brilliantly. And we still all today use all that data on all the zodiac stuff. But for all that 2,000 years, it was absolutely believed that the earth was sitting still at the center of the universe. It's not crazy at all. It's totally reasonable, and it's totally productive. It just turned out to be not quite as productive or fruitful as saying, no, actually, the earth is not at the center of the universe. And then so Galileo says it's not. And then a bunch of people sort of catch on. I mean, or Copernicus, or a bunch of people are like, oh, I get it. The sun is at the center. But no, we're saying, no, it goes beyond that. There is no center. That's a deep, even when people got Galileo's idea, they didn't get that. So it's a very reasonable question. Like, we're overturning thousands of years of advanced thought when we say there's no center to the universe. But that's what we're saying. Okay, cool. Okay, all right. So from the sublime to the mundane, back to average acceleration. Okay, so total distance.
I'm just going to write quietly for a second so I can take a breath and so you can, but stop me if you have questions on these. Oh, oh. Okay, so those are the answers to the warm up. I hope you can see the basic two things are, once we're talking about like the vector quantities, displacement or velocity, then once we're talking about vector quantities, number one, negative sign or signs come into play. I mean, technically the distances I could have put positive signs on, I suppose. I guess I will. But once there was direction came into play, then the answers became negative because I labeled south as negative. Also, just note as a sort of personal habit, once it was like displacement and velocity, then I started using symbolic notation. Okay, we drew a picture. Okay. Okay, so that's that one. If there's questions, please ask them now. I'm gonna then I'm gonna flip the page and go. Okay. Now we start to get into some issues here. All right, so we're back to the topic of velocity. Now, all I'm saying, velocity is relative, velocity is relative, velocity is relative. Okay, but now even within that, any velocity we ever talk about is a relation, not a property. But now we're going to start making a distinction. We've been talking about average velocity, v with a bar over it. But now, okay. So everything we've said about velocity so far has been about average velocity. Displacement per time is average velocity. The velocity with reference to an interval between 2 points in space and time. Now we're starting to all of a sudden think about or talk about velocity at a point in time and therefore at a point in space. Now so notice we're now moving to v without a bar on it. It may sound like we're going backwards, but we're not. V without a bar on it is technically instantaneous velocity. Velocity at an instant. Well, what is that? I could go on all day about this. I won't, at least not today. It's a tricky notion. If it's how what it is how fast a car, how fast anything is going right now, not over an interval, but right now. Now that's weird. That's weird because if we're talking about right now, if we're talking at a point in time, we're talking about how fast something's going. There's no interval of time between the two dots on the timeline. There's just a dot, right? So if our concept of velocity, if our concept of like average velocity was displacement over time interval, right? But if our time interval is 0, then first of all, that's a big problem because we now have 0 in the denominator, right? Second of all, in no time, of course, something goes nowhere, right? Like if you take a snapshot of a car, like while it's zooming down the highway, and you ask how fast is the car going during this snapshot? Well, I mean, if you ask how fast is it going during the snapshot, the reasonable question to ask is, well, how far did it get in that snapshot? But of course, how far it got was nowhere. So by this logic or this reasoning, V would seem to be 0/0 all the time, right? Bear with me for like, if literally velocity at a moment is just the concept of average velocity applied to a moment, that would be basically asking how fast is a car going in a snapshot or in a frame of a movie. And then the answer would always be 0/0. And that's a triple disaster. You could write in your notes. I'm not going to write. 0/0 is a triple disaster of well, really quadruple disaster of an answer. Please put this in your notes. If we just leave it that instantaneous velocity is average velocity, where we plug in 0/0, that is a quadruple disaster. Can't be right, because, and I'm sure you can see where this is going. I'm just going to say it anyway because we're running out of time. First of all, anything divided by 0 is undefined or infinity or explosion or whatever. So that's not good. Second of all, 0 divided by anything is 0. So that's not good. Like we're saying that it's always like no matter what, a car is never moving. Like at any given moment, but in a snapshot of any frame of a movie, a car is not moving at all. But yet you put all the snapshots together and you get a movie where the car is moving. So how could a bunch of zeros added together get you something? So 0/0 either is a blow up and says there's infinite motion, or it says there's no motion, or 0/0. Remember, what is 7 divided by 7, or x, any number divided by any number? X divided by x is always 1, right? So then by that reasoning, we would get 1 all the time, that every object all the time is going 1 mile an hour. Like what? No. And why I say that's 3 bad things about this idea. And the fourth is that whatever you interpret 0/0 to be, if you interpret it the same way every time, then no matter what, we're saying nothing ever has a unique velocity at a moment. That somehow everything's always going the same speed at any given moment, but you add up all these moments together and you get some kind of velocity. That makes no sense, I'm saying. So this is why we start our physics analysis with average velocity. I think, remember, I warned you, average is something we can picture, observe, measure, and compute. But it's not precise, it's an average. What we really care about is something precise, like velocity at a moment, but it's a lot harder to get our minds around. So we don't do it this is not a student teacher thing. This is like a physicist thing. We consider average velocity first as a way of entering the world of space and time. And then we try to adjust average velocity to get a concept that there must be. I mean, motion must happen at a moment. Otherwise, motion never happens, if that makes sense. Like motion happens through movies of life. So, and movies are just made up of a bunch of snapshot moments. So something must be happening in those moments. So how do we know? And these are just notes here. This is not 5-step, and this is just me talking. I guess that's why it's in yellow, maybe. Okay. Right. If my little rant right now, so I'm still on question 2, was to convince you that We don't have an equation for instantaneous velocity yet I'm about to ask you a question about it. We don't have an equation. We never talked about it before. I'm right now, and I'm saying it is a tricky idea. But I'm saying right now, if you believe in the idea, if you just what I was just ranting was like, things must be moving at each given moment if they're moving at all. So there must be a constant. And look, if any of you have ever driven and you've ever been pulled over by the police, I hope not. You know, they say, do you know how fast you were just going? They don't meet, like if I get pulled over by the police and they say, sir, you drove through a school zone, you just drove by like a school with little children. Do you know how fast you were going when you just went through the 20-mile-an-hour school zone? I can't say to the police, well, officer, I was in my car for the last hour, and I took 2 pit stops and like was in the right lane for a super long time. And I've only traveled a total of 3 miles in the last hour because I took all these pit stops and I was in the bathroom forever and then I was in the right lane. So I've only traveled 3 hours total in the last, I'm sorry, I've only traveled 3 miles total in the last hour. So on average, my velocity was 3 miles per hour. So I don't see what the problem is, officer. Like, I can't say that. I mean, I can say it, but that's not the officer's point, right? The officer's point is a point. The officer's point is, no, I'm not asking about your freaking average over the last hour. I don't care about that. I'm saying right at this moment, when you passed the school, you were going bleh miles and you were going 60 miles an hour. And by the way, that doesn't contradict anything you just said because yeah, it averaged out to 3, but I'm concerned with that point, right? There's got to be meaningfulness to how fast I was going at a point. If you even believe that there's meaningfulness to it, use context. We use context to get how fast we were going at a point. The ultimate context is calculus, but we build the calculus and that will happen sort of in the next couple of problems, but we build the calculus and we see the calculus from simpler examples where we didn't even know it was calculus when it was happening. For example, this one, like if we look at context on the next page, so I'm still in 2 continued. Again, I should be doing the 5-step method now, but I'm sort of I'm just gonna continue the way I'm going. Like here, well, here's you can fill in the other steps. Here's step 3, GDP is I say, okay, average velocity is defined to be displacement over time. This is not what the problem's asking. It's not asking for average. It's asking for instantaneous. But I know how to do average, so I'm going to write that down as my GDP. That's a truth. That is true before this problem begins, even though it's not ultimately what the problem's asking. But hopefully, I'm going to see a way of getting from here to there. So the average is 40 miles, and it does so in 0.5 of an hour, right? So I'm sorry. So the average, and this is already now in step 4. So what I've concluded so far in step 4 is that the average velocity is 80 miles per hour. The average velocity is 80 miles an hour. Now, that's not my final answer. It's not what it's asking for. It's asking for instantaneous velocity. But I also know that whatever the initial velocity was is the velocity at any given point. This is important. In this case, I was told 2 facts. One fact was the velocity, it was the average velocity. Sorry, one fact was the space and time coordinates of the car, like 30 minutes, 40 miles. But the other key fact that doesn't look like a fact because it doesn't have numbers. It's just English. It looks like a concept, but it's a key fact, is that the car's velocity is constant, which if I want to write in notation form, and I will do this for the rest of our lives, if I write V naught equals V, that is a notational or symbolic way of saying whatever you started with, you keep going at every, like whatever your instantaneous velocity at every single moment is your initial velocity. It's always the same, right? So if that's true, thus, in this case, or I could say, I could even have put, when V naught equals V, then V naught equals V bar. Like you, even when I just wrote here, I could have written from here on in, I could write it as a step 3 GDP. And I hope you see what I'm doing here. Again, it's all part of, I'm writing something down that many of you might have thought was so obvious. It's so clear to some of you in your mind that you wouldn't even bother to write it down. You think it's like too obvious to even like, but I'm saying, no, wait, this is a concept that can be symbolically notated. And all we do in physics from here on in is we just keep taking things that seem obvious and then we symbolically note them so that we can use them later as they get less and less obvious. Okay. So nothing is really actually obvious, and what's really not obvious is what's important. So what I'm saying is important is if something has a constant velocity, then its instantaneous velocity at any given moment is the same as its average velocity. Notice I'm not saying you may want to stare at this later in your own private INO, what I just wrote here in yellow. Like this is where, okay, and again, for some of you who already had this straight, you might think that I'm making it harder than it is. I'm just trying to show you how physics works. Like V and V bar are not the same idea. They are defined differently. They two different meanings behind instantaneous velocity and average velocity. They're both velocities. They're both relative, but one is at a point and one is over average. Now, over an interval. Now, however, they can have the same value. They don't have a triple equal sign linking them, but they absolutely can have a double equal sign linking them when and only when velocity is constant. So therefore, in this problem, I wish I could change these favorites around. I don't know. Therefore, so here then, the answer is okay. Sledgehammer ant. I'm sure many of you got this right without writing all that down, and that's fine. Bottom line, the answer to the question is 80 miles per hour. The instantaneous velocity at the 18th minute, 42 second, was 80 miles an hour. The thing I want you to take away from this, and again, I'm proud, I'm sure many of you got it right, and that's awesome. It is. But a couple things to note. First of all, note that the 18th minute, 42nd second like sounded arbitrary and intimidating, and it sounded like something very specific you had to deal with. But if you really understand the problem, you don't have to deal with that. Like it doesn't make it any harder. Number two, note I asked you a question about some new concept called instantaneous velocity. but we didn't have a formula for it. We actually will in a moment have an equation for it, but even without an equation for it, if you think it through, you can still get it, right? And that's what, and so the equation then hopefully is going to capture what your thinking was anyway, not the other way around. You don't think from equations, you think to equations, if that makes sense. But number three, notice if you did this problem and you literally just like did 40 divided by 0.5, 80, okay, that's my answer, and then moved on. If you didn't even have a bump or a moment where you're like, wait, but is that what it's asking? Or is that like, then that would be wrong. And if you put it on an exam, if you just wrote V bar equals 40 over 0.5, or V equals 40 over 0.5, therefore answer 80, that'd be wrong because it's not that straightforward. Like 40 over, so again, tell me in the chat or with a phone call or something like that you're missing what I'm saying right now, but it's not. I wrote more than you need to, but you might have written less than you need to if you just wrote 40 divided by 0.5, because that by itself is just the average velocity, and that's not what we're asking for here. Okay, but the answer is 80, so that's the answer to that one. Okay, babble. I'm just looking at the chat again. Hold on a second. Pardon me. Okay. So I know we only have 5 minutes. Whoop, hello. We only have 5 minutes. All right, I'm going to quickly. So now we're going to get. Oh, well, even if we don't get to the next. So what is the equation? Okay, with only 3 minutes left, I'm going to choose to do this rather than finish problem 3. I'm going to give you 2 more equations really quick with 3 minutes left. The thing you're supposed to see in that last problem, as always, is like that's like the simpler version of the larger concept. Simpler version is to know what's happening at a point. You look at the whole and you zoom into that point. Now, in this case, it was easy because the whole was constant. If you were picturing on a graph, the whole was a horizontal line. And you were looking so all the points had the same status, the same value. What if the graph is like not a horizontal line? What if it's like a diagonal line, or God forbid, quark forbid, a curve? What do we do then? Well, same thing. We look at the whole thing and we zoom in. But what is it called to zoom in? What is it called to take, say, the slope of a graph at a point? It is to take the slope of a graph between 2 points and shrink the interval of those 2 points until they are arbitrarily close to each other, right? In other words, and you know where I'm going with this, how we do this in general is we take a limit, which is called a derivative, right? In general, I'm saying this fast, but I mean, I think many of you already know this, but I'm just also trying to put perspective on what a derivative is. In general, what V is, well, what it really is what instantaneous velocity is average velocity, but the average velocity between 2 points on a graph, but taking to the limit as the 2 points get arbitrarily close to one another. Closer and closer so that our precision is higher and higher, but not so close that they're literally on top of each other, because then we'd have 0. It's as close as we can get to 0 without being 0. And what does that mean in science? That means 2 points that are closer together than any measuring instrument can detect. That's what it means. A limit is very real in science. It's not a hypothetical. It means smaller than anything we can measure, but bigger than zero. Big enough that it has a quantity, but small enough that we can't distinguish that quantity from other quantities. That's what it means. So instantaneous velocity is the limit as t goes to zero of average velocity. In other words, so this is a new equation now. And we have 1 minute. I'm going to end on this. Oh, sorry. It's literally this, like the slope of the tangent line on a position time graph, if that makes sense. We'll talk more about that on Tuesday. Oh, yeah. So in other words, the last thing I'm saying, so in other words, what V is from now on is dx dt, the derivative of position with respect to time. I think that's a question, but hang on 1 second, because I know we have to, now, really quick, that's a concept. That's true, and that's the link from physics to calculus. It means you have to do calculus to do physics sometimes. It doesn't mean you can plug into that equation simply and get answers, but it's a concept. Now, wait, Andy has her hand up, but it's 12 of us. So what I'm going to do is I'm going to say, Andy, hang on for a second. If you don't mind, everybody else, or anybody else who wants to go. I'm going to turn off the recording. We're done, but I will hang out for a second and answer Andy's or anybody else's question. It just won't go on but thank you and we'll keep doing this. Just keep working on this for Wednesday. Well, okay. And I'll hope, okay. Stopping the recording. Okay.